to make sure we stay on track and still have time to review before the exam, we're just going to get started, but we'll be doing some drawing and thinking partway through lecture today. So we're continuing talking about transport of gases in the blood today. We touched very briefly on about the first slide of this on Friday. So if we recall, we're talking about how we can transport our gases, oxygen and carbon dioxide through the blood. And we know this is important because we know we're exchanging these gases at the lungs and we're exchanging these gases at the respiring tissue. So we also want to know how they get from place to place. And there are some complicated kind of factors that influence how much oxygen, how much carbon dioxide we can actually hold in our blood. So we saw, this is the one slide we went over, that oxygen is mainly transported by hemoglobin. It's not very soluble in the plasma, which we noted, right? It's its ability to dissolve into water wasn't very high. Right? It's not very soluble. Plasma is mainly water. So only about 1.5% of the blood oxygen is actually in the plasma, and the rest is going to be transported by hemoglobin in our erythrocytes, which are our red blood cells. So far, hopefully so good. We've talked about hemoglobin briefly before when we talked about the life cycle of a red blood cell. Okay. So the way we're going to express this when we're writing equations, which we will see multiple times today, right, is we're saying Hb, that's our hemoglobin, plus O2. This is when they are separate from each other, bound together, create oxyhemoglobin. That's what this Hb dot O2 is. That's telling you that's hemoglobin bound to oxygen. So Hb on its own, we refer to as deoxyhemoglobin because it doesn't have oxygen. And then this HbO2, we refer to as oxyhemoglobin, telling us that it has oxygen bound to it. So hemoglobin has 4 spots where it can bind oxygen molecules. So we see them here on this image, right? They're binding to our heme groups. Remember that we have 4 globin bits of hemoglobin, and we have 4 heme groups that contain iron. So here are the 4 oxygens we're binding in to our hemoglobin. So like other things in this class, the binding of oxygen to hemoglobin is following the law of mass action. So that basically just says if there's more of something, that reaction is going to proceed in basically the right direction, right? More of oxygen creates more binding of oxygen to hemoglobin. So actually, I'll flip back to the previous slide, right? So what we're saying are those scribbles. I'll come back to them. All right, so we're saying if we increase oxygen on this side of the reaction, this forces this reaction to go to the right. And that's our law of action. Okay. So since hemoglobin has 4 spots for oxygen, we are also going to think about how saturated the hemoglobin is, because we're not always going to have our hemoglobin be either empty or full. We're going to see that often it has some of these 4 spaces filled, but not all of them. Okay, so the saturation of the hemoglobin is kind of a measure of how much oxygen is in your bloodstream, but specifically it's a measure of how much oxygen is bound to the hemoglobin. Okay. Some other terms here that we want to keep an eye on is loading and unloading of oxygen. So we're going to be tracking what causes basically easier or harder oxygen loading versus unloading. So when we say that O2 is loaded onto hemoglobin, we're saying you gain an oxygen on that molecule. When we say it's unloaded, what we mean is that we're taking off the oxygen, and that oxygen is going out to some tissue, right? So to some respiring tissue, to some cells that need oxygen. Okay. So we're going to expect that O2 on the whole is going to be loaded onto the hemoglobin in the lungs. It's going to be unloaded in the tissues, but we're going to be looking at some things that influence the rate of both of those processes. So this image with four oxygen molecules on it is 100% saturated, but we're going to see that that's not always going to be the case for all of our hemoglobin in the blood. Okay, so now we're looking at some steps of O2 transport in the blood, and I just want to key us into some pieces on this image. So instead of drawing out our hemoglobin here, we just have these boxes. So this is just showing us the 4 slots for oxygen in our hemoglobin. So that's what that diagram is, and what we're looking at is the inside of an erythrocyte, so inside a red blood cell. Okay. So when we talk about the O2 carrying capacity of blood, we're talking about how much oxygen it can carry. And when blood is 100% saturated, meaning that all 4 of those spots, right, are filled up, right? Each hemoglobin is carrying 4 molecules of oxygen. A 1 gram of hemoglobin would carry 1.34 milliliters of oxygen. And you worked with these numbers in phys lab, actually, back in A&P1. Your normal blood hemoglobin levels are about 2 to 17 grams per deciliter, giving you 200 milliliters of oxygen per liter of blood. And you have about 5 liters of blood going through your system at any given time. Okay. So when we compare arterial blood to venous blood, we are going to see that we have different saturation of our hemoglobin, which makes sense, right? We think of arterial blood coming from the heart as our oxygenated blood, and our venous blood has already passed the tissues, right? So it's already unloaded some of its oxygen. So this set of images on the right, is showing us the difference between our arterial blood, which we know has a partial pressure of 100 millimeters of mercury, right? That's our pressure of oxygen in arterial blood. And that's representing about 98.5 saturation of hemoglobin, right? So they're almost all full, these hemoglobin molecules. When we look at the venous blood, that's not the case. So we know our venous blood, our partial pressure of oxygen drops precipitously, right? We lose a bunch of oxygen as we go past the tissues and into the veins. So our partial pressure is down to 40. And a partial pressure of 40 millimeters of mercury for oxygen would give us about 75% saturation of our hemoglobin. So that's why we see these empty spots in our little boxes. That's telling us that the hemoglobin has essentially lost 25% of the oxygen. So that brings us to our hemoglobin and oxygen dissociation curves. Okay, so what this is showing us at the moment for this first curve is on the bottom. Okay, so on the bottom here, we're looking at our partial pressure of oxygen, right? So we know that at 100 as our partial pressure, right, from that previous slide, we know that we are almost at 100% saturation of hemoglobin, and that's true of our arteries, right? Okay. Conversely, the other data point we have so far, right, is that at a partial pressure of 40, we know that's what we have in our veins. Our oxygen is our hemoglobin is about 75% saturated with oxygen. So those 2 points are the example we just looked at. So what we can see from this curve are several kind of additional facts about the relationship between oxygen and hemoglobin. Up here at the top, we have highlighted how much of the oxygen is unloaded by hemoglobin to the tissues, right, is the difference between the systemic and the venous saturation of hemoglobin, right? That's what's on our left. But the shape of this curve is actually very characteristic. So this is called our hemoglobin oxygen dissociation curve. Okay. Title it up here. Hemoglobin oxygen dissociation curve. Okay, I'll try to get that nice on top. Okay, so what we can see here is that at the beginning, when we start out at very low saturation and very low pressure of oxygen, right, that those two are linked, right? If we don't have much partial pressure of oxygen, there isn't a lot of oxygen. So therefore, there isn't a lot of oxygen to saturate the hemoglobin. But a cool thing that's true about the relationship between hemoglobin and oxygen is that as soon as you have a molecule of oxygen bound into that first spot on your hemoglobin, right? So if this is our hemoglobin, as soon as you have one molecule of oxygen in there, it actually makes that hemoglobin like suck up more oxygen. It increases the affinity of hemoglobin for oxygen. So that's the reason for this rapid rise. That's why we see this very sharp slope from this low level at about pressure of 10 up to this venous partial pressure of 40. This is because as we start to have one oxygen bound into our hemoglobin, that makes it super sticky, so it rapidly pulls in the additional molecules of oxygen. So it saturates pretty quickly. So this curve is a specific shape, and the next couple of things we're going to be looking at are things that shift this curve either to the right or to the left. Okay, so we want to remember the shape of this curve. Okay, so we're going to draw those shifts out. Oh, where'd my annotation tool go? Okay, did want to keep that title. So we're going to be thinking about our hemoglobin O2 dissociation curves. So whenever we're looking at these curves, we want to start with our axes, right? So we know that we're looking at the pressure, partial pressure of oxygen on the x-axis. Okay, so PO2. Okay, and on our left axis, sorry, our y-axis, on the left side, we're looking at the O2 saturation. Okay, so our normal curve, we know, starts out low, right? But then has this rapid rise, right? Hits the venous blood pressure, partial pressure of oxygen at about 40, and then starts to kind of slowly flatten off as we get to our systemic artery pressure of 100. Okay, so we have our points of about, pick a different color for this. Right, so let's say this was our venous pressure, and here we have our arterial pressure. Right? So we've got like 40 and 100 here. 100, we got 40, and we know our points. Sorry, everybody, a little bit messy. So we know that this is going to correspond to about 75%. And then this higher part is going to correspond to about 100%, right? Like 98.5, but let's just round up. So when we talk about a right shift versus a left shift, what we're talking about, I'll draw the right shift first. What we're saying, oh, I wanted a different color. Okay. What we have, if we have a right shift, is we're literally moving this curve over to the right. We could still reach 100% saturation eventually. So our curve will have the same shape. Sorry, I'm not the best drawer, but that's the same shape, but it's moved over. So what we're saying here with a rightward shift is that to get the same concentration, or sorry, to get the same saturation, right? So if we wanted 75% saturation, we'd need a higher PO2. Right, so we'd have to have a higher partial pressure of oxygen to reach the same saturation. So what that basically means, right, is that it's harder to get oxygen onto those hemoglobin, right? So if we talk about a right shift, and I'll write it out right here, some of our facts here. So a right shift is going to mean that we have lower affinity for O2. So we have lower affinity for oxygen, which means it's harder to get oxygen loaded, right, onto the O2. So harder to load, harder to bind, load O2. But the cool and useful converse of this is that it's easier to get the O2 off. So we're going to say, right, it's easier to release or unload O2. And this is going to be really useful for us because we don't just want to get oxygen onto our hemoglobin, right? Like it's nice to have a high O2 saturation running around in your blood. But the whole point of carrying that oxygen is to release the O2 at the tissues. So while this right shift making it harder to get O2 onto the hemoglobin may seem like a bad thing, it's actually something that we need to have happen in certain cases in order to get that oxygen off of the hemoglobin and into our tissues that are actively respiring. So we have specific factors that are going to affect our shifts. And I'll go ahead and make some notes now, but we're going to talk about them as we go through. So one of the examples of why this might happen is changes in temperature. So a higher temperature creates a right shift. Other things we might see are changes in pH, so low pH will cause a right shift. Increases in CO2 cause a right shift. So do increases in something called 2,3-BPG, which we'll see is particularly associated with altitude. So we'll take a look at that in a bit. Okay. We can also have a leftward shift, right? So if we can move something one direction, we can move it the other direction. So if we move this curve in the other direction, and a leftward shift, we're saying basically all the opposite things, right? So our right shift was a lower affinity for O2. So our left shift means we have a higher affinity. So, and we can see how that's true, again, if we compare our points, right? Now, to reach this 75% saturation, we didn't need as much of a partial pressure of oxygen, right? We got there faster, okay? So basically, we'll see the converse of these characteristics happening to create this. One of the important ones really for the left shift is this temperature. So if we have a higher temperature for a right shift, right, an example of why we might see a left shift is a lower temperature. Okay. And this isn't just true like fever versus non-fever. This is also like locally true. So out at respiring tissue, right, where we're using the oxygen, we'll often have a higher temperature, right? You can think of that like as your muscles are working, right? You start to heat up, right? We all know when we exercise, we get hot, we sweat, right? So you have a higher temperature often at these respiring tissues, making it easier to unload O2. But often in the lungs, we'll have a lower temperature than at the tissue, meaning that we have a higher affinity for O2, making it easier to load the oxygen onto that hemoglobin. So this can vary throughout our system as well. Okay. I don't think I used the specific word for this sharp slope at the beginning, so I do just want to point out that we do have a word for it. So what I was talking about when I was talking about this sharp region, right? So this stuff, right, this sharp slope where when we have one oxygen bound, it makes it easier to bind more. This is called cooperative binding. And cooperative binding. Okay. Right, like it's like our oxygen molecules are cooperating together to get that hemoglobin full. Sorry, I keep grabbing this blue pen by accident. Okay, but this sharp region here was our cooperative binding. Okay, I know this looks messy. Questions at this point about this hemoglobin oxygen dissociation curve? Because what we're about to get into are basically all the kind of little fiddly bits that change this curve. So I want to make sure that we understand the original curve to begin with. Okay, as we move forward, if we get confused, that's fine, just let me know. Okay, so now we're thinking about oxygen transport in the blood. So we've seen this dissociation curve, right? This dissociation curve. We know we have our standard dissociation curve, where our standard partial pressures of oxygen in the tissue versus in the lungs give us 75% saturation near the tissue, 100% almost saturation in the lungs. But now we're thinking about the causes of those right and left shifts to the curve. So when we have an effect of pH on that dissociation curve, remember that basically a lower pH gives us a rightward shift. Okay, and what that means is that lower pH or acidity basically increases O2 unloading, so it makes that oxygen more available to the tissues, but conversely would make it harder to bind O2 onto the hemoglobin. So the name for this is the Bohr effect, this effect of pH on the affinity of hemoglobin for oxygen. So Bohr effect equals a right shift equals lower affinity. Okay. So This is neat because one of the places we're going to see this is in our active tissues, right? Our active tissues actually produce more acid. So our pH is going to be lower in the tissues than it is in the lungs. So this decreasing pH causes a shift to the right in that saturation curve, meaning that oxygen is unloaded more easily, meaning we can get that oxygen into the tissues. Our next named effect is called the Carbamino Effect. So the Carbamino Effect is the effect of carbon dioxide on hemoglobin and its ability to carry oxygen. So we actually have an equation for this, by which I mean a chemical equation, right? So we're saying that hemoglobin and carbon dioxide together can form this molecule called Carbaminoheboglobin. And Carbaminoheboglobin has a lower affinity for oxygen than hemoglobin on its own does. So it can still carry some oxygen, but not as much. So when we have a lower affinity, that's a rightward shift, okay? So we can see that when we have a bunch of carbon dioxide, we're creating Carbaminoheboglobin, we're lowering the affinity. That's basically going to make it easier to get oxygen off our hemoglobin. So like with the Bohr effect, we're going to expect to locally see this effect near the tissues because increased metabolic activity, right? When we talked about metabolism, right? We know that an effect of glucose metabolism is we get rid of carbon dioxide, that's our waste product. So locally, we're going to have a lot of carbon dioxide near the tissues, reducing hemoglobin's carrying capacity for oxygen. Okay. So our next factor that affects this is this molecule 2,3-DPG or 2,3-BPG. For our purposes, we can consider those equivalent. We don't need to know this name, but it's diphosphoglycerate. So the diphosphoglycerate, 2,3-diphosphoglycerate, is produced in red blood cells when there's low oxygen. So different things can cause low oxygen. Anemia can cause low oxygen, right? That's actually kind of our definition of anemia, is that we're not able to carry enough oxygen. But other things that can create low oxygen environments are things like high altitude. As you go up, you've heard some people get altitude sickness, right? That's partially because we're going to have lower O2 when we get really, really high above sea level. Okay. So BPG synthesis is inhibited by oxyhemoglobin, which is why we only see this effect under low O2 levels. And this 2,3-DPG molecule decreases the affinity for hemoglobin, right? So it's a rightward shift, meaning that it's easier to get O2 off of our hemoglobin and into our tissues, right? And this is helpful because if we have low O2 to begin with, right? If we had our sort of normal level of how hard it is to get O2 off, this effect would kind of be compounded, right? Like we wouldn't have enough oxygen to begin with, and then it's also hard to get that oxygen off the hemoglobin. This would make our situation a lot worse. So this is why it's important that under low O2 environments, this kicks in. So here we can see the curve for that. So here our blue curve, right, we can see is a rightward shift, basically. Carbon monoxide also affects O2 transport. Basically what carbon dioxide does is that, or sorry, carbon monoxide, the reason it's so dangerous is that hemoglobin would rather bind carbon monoxide than it would O2. They're basically competing with each other for those spots on the hemoglobin. So hemoglobin has a greater affinity for carbon monoxide, we would say scientifically. But if our spots on the hemoglobin are filled up with carbon monoxide, right? If we have our 4 spots, right, and suddenly we have carbon monoxide occupying a bunch of them, right? We do not have enough room for O2. And this is why people die of carbon monoxide poisoning, right? Even if there is enough oxygen in the environment around them, if there's carbon monoxide in that environment, it's going to hog all the hemoglobin, so we won't be able to get oxygen to the tissues, even though it's present in the air. So this is why it's so dangerous. Okay. So if we want to think about a question, and we'll do this pretty quickly. So imagine that you were hanging out in New Orleans, right? You were on vacation, and then you decided to, for your next step of the vacation, go climb a mountain. What do we think this is going to do to our dissociation curve? Okay, looking pretty good. Yeah, this would create a right shift, right? So as we reach altitude, right, at high altitude, and especially if you're altitude adapted, so people can get used to high altitudes as well, right? People who are adapted to those environments don't get altitude sickness, right? If you live on the top of a mountain, that wouldn't be terribly helpful. So we can see that as you adapt to the altitude, you have more BPG or DPG, the 2,3-DPG that we were looking at, compared to normal. Right, here we have normal, here we have absolutely no BPG. So we can see that this is a rightward shift, making it easier to get oxygen into the tissues. So now we want to talk about carbon dioxide, because as it's important to get oxygen to the tissues, it's also important to take carbon dioxide away from the tissues. We've also seen, right, that there's kind of this trade-off already between carbon dioxide and oxygen when we're thinking about what the blood can carry, right? Because we know that carbon dioxide, when there's a bunch of it in the blood, this is basically preventing hemoglobin from carrying as much oxygen in the first place because of that Carbamino effect. So we'll get to a kind of opposite effect that our oxygen has on carbon dioxide transport as well. Okay. But usually what's happening with carbon dioxide is that we're going to use this enzyme carbonic anhydrase, which we talked about as being present in our red blood cells when we were talking about red blood cells before. And carbonic anhydrase is basically going to convert our carbon dioxide into a form that can be carried in the blood. And we'll take a look at the equation in a second. So carbon dioxide exchange and transport is happening in the systemic capillaries, also happening in the pulmonary capillaries, and we're carrying that carbon dioxide mainly in the veins. And we are going to see that there are effects of oxygen on carbon dioxide transport. Basically, right, we have this trade-off: more oxygen, less carbon dioxide; more carbon dioxide, less oxygen. They have different names for these opposite effects, but it's pretty nifty that they're this trade-off. Okay. So we can see, if we look at our arterial versus venous blood, we can see where our carbon dioxide is, which is mostly going to be dissolved in the blood, not as carbon dioxide itself, but as this molecule called bicarbonate. Okay, and this is going to be important now, and it's also going to be important when we get into the renal system next. There are other places we see carbon dioxide. We do see some directly dissolved in the blood, right? So directly just hanging out in the plasma. We do see some bound to hemoglobin, not to the heme group. It's not competitive with oxygen the way that carbon monoxide was, but it can bind onto hemoglobin as well. But most of it is going to be dissolved as bicarbonate. Okay. Yep. Oh yeah, nifty that I added this. Okay, so another thing we want to remember is that more carbon dioxide can be dissolved in plasma than O2 because it's more soluble in liquid, right? We talked about the solubility of O2 versus carbon dioxide last week. Okay, but still mostly in bicarbonate, so we want to think about how we get there. Okay, so we're using this enzyme called carbonic anhydrase, right? What carbonic anhydrase does is it takes carbon dioxide plus water and it creates carbonic acid. Okay. We're not done once we get to carbonic acid though, because what happens to carbonic acid, here highlighted at the bottom, carbonic acid can then in turn be split up into hydrogen ions and bicarbonate ions. So we could think of this as a whole kind of potential flow, right? And then like this. Okay. So when we think of carbon dioxide, we think of it as basically a biological acid because of this final step, right? This final step produces acid in the form of these hydrogen ions. Okay, so most of the carbon dioxide that's in our blood has actually gone through all of this and is in this final form. So anytime we have changes to the carbon dioxide content, like with all other chemical equations, they're going to follow this law of mass action. So if we increase carbon dioxide, right, this pushes the equation to the right. So if we increase carbon dioxide, it's going to in turn increase our carbonic acid. And if we go to the bottom, if we increase this carbonic acid, right, this increases our bicarbonate and hydrogen ions. And the presence of hydrogen ions basically is what we create acidity with. This is what lowers the pH. Okay. So that's what's happening as we're carrying carbon dioxide, and this is why the idea of carbon dioxide being present is also going to be kind of considered as lowering the pH as well eventually, especially in our other units. Okay. So we said that there's a trade-off between carbon dioxide and oxygen. And when we were looking at it from oxygen's point of view, right, we were thinking about that as our Carbamino effect, the fact that carbon dioxide bound to hemoglobin has a lower affinity for oxygen. The opposite is also true. This is technically called the Haldane Effect. I'm not too concerned whether you know that specific name or not. But what we're seeing is that when we have a high partial pressure of oxygen, our total blood carbon dioxide is relatively low, right? So this is like our arterial blood that's fresh from the lungs getting pumped into our systemic arteries, right? High partial pressure of oxygen is part of what is keeping carbon dioxide low there. As our partial pressure of oxygen goes down, right? Goes down. This is our thick blue. Okay. This is our partial pressure of oxygen as we're leaving the tissues, going through the veins, right? We can see that it's slightly easier for us to carry carbon dioxide. And if we got all the way down to zero, it would be even higher. So we just have this trade-off between basically how much oxygen there is and how easy it is to carry carbon dioxide. Just like when we had a lot of carbon dioxide, it was harder to carry O2. Okay. So these charts are a little terrifying, but they're just saying the same thing. So we have one for what's happening at the tissue and one for what's happening at the lungs. So here we're looking at I thought we had the tissue first. Did I skip a slide? Okay, yeah, I did skip a slide. Sorry, guys. Okay, so here we're looking at what's happening in tissue, right? And I'm actually going to start us at the bottom because I think that's more helpful. So what we want to have happen in our tissue is we want to release oxygen because we want that to get into the tissue. So the way we're going to do that is we are going to physically take oxygen off of the hemoglobin and put it into the tissue. So this portion that says direct effect, right? This is really just talking about that unloading directly, right? If you take oxygen off of the hemoglobin, that is lowered partial pressure of oxygen because that's going into the tissue. So that by definition, that kind of is defining our O2 unloading. So those are just saying the same thing. The way we make it easier to unload that oxygen is by lowering the affinity of hemoglobin for oxygen. And we can do that by changing the pH, which is the Bohr effect, or through the Carbamino effect, where we are binding that carbon dioxide onto hemoglobin, making it have lower affinity for oxygen. Both of those help us unload oxygen from our hemoglobin. Okay. And we can see that both of these are at least in part due to high amounts of carbon dioxide. We've seen that carbon dioxide can, in kind of two steps, be converted into hydrogen ions and bicarbonate ions. So it does increase our hydrogen ions, which lowers our pH, making more acidic, lowering hemoglobin's affinity for oxygen. And if we have higher CO2, that is also going to create more carbon dioxide loading. Okay. So when we have hemoglobin and carbon dioxide bound together, that's the Carbamino effect. Okay. This Haldane effect is just telling us from that previous slide that when we have lower PO2, it's even easier for us to have lots of CO2. Okay. So conversely, at the lungs, we want the opposite to happen, right? So at the lungs, we want to load oxygen, right? So we have a high partial pressure of oxygen as we're breathing in, reaching equilibrium with that partial pressure of oxygen in the alveoli, creating O2 loading onto the hemoglobin, right? And we have our effects increasing hemoglobin's affinity for oxygen. And these two pathways are just the opposite of what we saw in the previous one, right? So instead of having higher hydrogen ion concentration, we now have lower hydrogen ion concentration. Lower hydrogen ion concentration, instead of having a rightward shift when we had higher, has a leftward shift when we have lower. And here when we have less CO2, right, we're not going to have this same effect of the bound carbon dioxide and hemoglobin, which was part of what was preventing us from binding oxygen effectively in the tissues. So this is really just the opposite of the other drawing. Okay. So now we're briefly going to go into regulation of ventilation, which is where we were supposed to be today according to the schedule. Okay. So we're thinking about what is actually controlling our rates and patterns of breathing. So this is going to involve the central nervous system. So we're going to see that control of breathing is controlled by neurons, right? So we've seen some of the nerves that control our muscles associated with breathing in the lab. We're going to be thinking about those, but now we're also going to be thinking about what's going on in the brainstem to cause our breathing rhythm, and also what kind of input we're getting from peripheral respiratory centers, giving us information about what's going on in our body, telling us basically whether we should start breathing faster or whether we need to slow down. Okay. So when we're thinking about controlling our breathing using our motor neurons, what we're thinking about are our respiratory muscles, right? Motor neurons go to skeletal muscle, right? That's what a motor neuron does. So our respiratory muscles here are our skeletal muscles. They're controlled by our motor neurons. And specifically, we know that inspiration, so breathing in is happening because we are lowering the diaphragm, right? When the diaphragm contracts, it presses down, increasing the size of the thoracic cavity, which drops the pressure, which allows us to breathe in. We're also contracting our external intercostal muscles, which is basically making our chest wider and deeper, again, increasing the volume of the thorax, and therefore decreasing the pressure. When we decrease that pressure down below atmospheric pressure, we have airflow down that pressure gradient and into the lungs. So the diaphragm is controlled by the phrenic nerve, and in lab, you either have or will see that attachment, that nerve going directly to the diaphragm. Our external intercostal muscles are controlled by spinal nerves, basically. So they have a specific named external intercostal nerve. The phrenic nerve is special and has a special name. And you may see it again if you start to talk about like spinal cord injuries. It's actually coming from up in your neck originally. So when we have injuries to the neck, often what we're concerned about is damage to the specific portions that control this phrenic nerve, which happen to be C3, C4, and C5, because it's a big problem if we can't control the diaphragm independently anymore. That would mean someone's not able to breathe independently, which is often fatal, right? So spinal nerve injuries can cause paralysis of various parts of the body, but if they paralyze the diaphragm and you can't breathe, that's the biggest of problems. Okay, so expiration is also caused by motor neurons. We do want to remember, just from before, that expiration is usually passive. So usually it's just our diaphragm and external intercostal muscles relaxing. So when we're saying that the internal intercostal nerve is stimulating the internal intercostal muscles, what we're talking about is forced expiration. So those are just additional notes right there. You don't need to memorize these depolarizations and stuff, but here we're just going to look at the difference between quiet breathing and active ventilation to kind of hammer that home. So on the top, we're looking at the phrenic nerve. In the middle, we're looking at the external intercostal nerve. On the bottom, we're looking at the internal intercostal nerve. So this is just emphasizing to us that during quiet breathing, we don't need that internal intercostal nerve, because this process is passive, so we don't need to use those muscles. But during active ventilation, when we're forcing our breath, right, when we're really huffing and puffing out, that nerve is going to come into play, because to forcefully expel air out, we do need to use those muscles. And here we just see what that would look like to muscle tension. So this is the same thing. It's just our diagrams on top are showing us what's going on in the nerve. At the bottom here, we're just looking at what's going on in the muscles as relates to that, right? And we remember from back when we talked about nerves, right? We know that if we send an action potential, right, which is a wave of depolarization, that creates contraction in our muscle. When it's not going, that's creating relaxation. Okay, so we will stop here for today and we will finish up with regulation on Wednesday. I'll see you then.
Thank you.
Yep, take care.